Hello, everyone, again. Again, welcome to the IEEE, the Undergraduate Academic Conference, being organized by our IEEE Turkey section. We are again in session 3, the morning session of Sunday. And we had a keynote speech, a lecture from Professor Çağlar Erbiken between 10 and 11 a.m. And now we will start the undergraduate student presentations. Our first presenter, by the way, let me also remind you that each presentation will take around 12 minutes and then we'll have around like 3 minutes for questions and answers session. So our first presenter is Mr. Muhammed Yusuf Efe from Boğaziçi University. And the topic of his talk is a vertical federated learning method for multi-institutional credit scoring, MICS. And yes, the word is yours, Mr. Yusuf.
Let me screen share. Can you see the screen right now?
Yes, we can see.
Okay, then let me begin. I am Yusuf Efe. I am an electrical engineering and physics double major student from Boğaziçi University. So let me start with my work. Okay, firstly, to give a brief introduction about credit score. When an applicant applies to a bank to get a credit loan from the bank firstly calculates a credit score related with the customer, and according to the score, they decided to approve or reject the application. And why is calculating the credit score is important? Because due to accuracy problems, there may occur so many false negatives or false positives during these calculations. And for example, if there are many false positives in these credit score calculations, they may lead to a big economic crisis, such as the mortgage crisis in 2008. And is it being calculated effectively right now? Now, in today's world, banks, due to data privacy regulations, banks uses only their own information. For example, if I'm a customer from a İş Bankası, then they have some features about me, and they can use only their own data about me to calculate the credit score. But however, in today's world, we are affiliated with so many different industries and so many companies, and our available data on the internet is actually distributed among different companies. So, but if one figures a way out to be able to use all the distributed data to calculate the credit score of that customer, it would be its accuracy would be higher. But due to data privacy regulations, these different companies cannot share the data they hold about these customers explicitly. So one should figure a way out to be able to use all the available data without violating any data privacy concerns. And this is the main topic of my research, actually. Firstly, let me briefly explain my data set used here. Firstly, let me introduce the concept of vertical split. Let's say we have a central data set, and in this data set, let's say there are totally 6 features. Each row corresponds to different customer here, and there are totally 6 different features for each customer. So in this vertical split, let's say ABC features are coming from telecommunication industry, and features D, E, F are coming from banking industry. So, and this is the vertical split. And as for horizontal split seen here, in each industry here for the telecommunication industry, there are different companies here, so that their data representations also differ. Let's say, for example, the feature A is the internet usage, while telecommunication company A may store this data as the for example, weekly internet usage in the unit of megabyte. Telecommunication company B may store it as the monthly internet usage in the unit of gigabyte. So actually, there may occur some data compatibility issues too. So for the overall of the data set, for example, in this data set, there are 3 different industries here, banking, telecommunication, and delivery, and there are 2 different companies, so 2 different data representations in each industry. So normally, for example, İş Bankası would use only its own customers and all own features to train a model. But in our system, we can actually make use of all different kind of customers. For example, in this row, there's a customer affiliated with Türk Telekom, also customer of İş Bankası, and also customer of Getir. this customer is being used with the customer in this line is affiliated with Vodafone, Yapı Kredi, and Yemek Sepeti. Actually, they are affiliated with totally different companies, but they both can be used in the same global neural network training without violating any data privacy regulations. And credit score is actually just a concrete example of my research. It could be applicable to any similar data set setting. So my proposed solution, I explained the data set like before. For example, in each for this row, there's a customer. The features are coming from Türk Telekom, İş Bankası, and Yemek Sepeti, and there are different kind of customers affiliated with different companies. So, like in the available data sets you can find on the internet, for example, in UCI global data set source, there are not actually many distributed data sets. So I should like find a way to actually mimic the real life scenario. So I used actually centralized data sets, but according to number of industries, for example, if there are 3 different industries, I randomly split features into 3 different groups to mimic 3 different industries. And for each industry, let's say for the telecommunication company, there are 2 different data representations, but in the centralized data set, actually both the Türk Telekom and Vodafone are coming from the same data representation. But to mimic the real life scenario, I should find a way to actually apply a transformation to the customers affiliated with Vodafone so that these data's prediction power wouldn't change, but their representations would be different. So I applied Gaussian random projection to each company's data so that now for the features from this telecommunication for the telecommunication industry, Türk Telekom and Vodafone have different representations. And now let me briefly explain the first stage of encryption. Like for each customer is affiliated with a telecommunication company. It may be Türk Telekom or Vodafone. By the way, in this concrete example, there are 2 different companies in each industry, but this is just an example. So it could have been 4 or 5. This is just an example. So let's go over this example. So each customer in this data set is affiliated with a telecommunication company, right? So we firstly centralize all these data in a telecommunication data server. But firstly, we need the first step of encryptions here. So we apply the PCA feed dimensionality reductions to each data, and after that we concatenated this with one hot encoded vector so that the global neural network actually can figure out where the data is coming from. Is it affiliated with like the telecommunication company A or B? If the data is coming from Türk Telekom, for example, we are adding 0, 1 to the end. If it's coming from Vodafone, we are adding 1, 0. And after that, we need the second step of encryption. And for this, we are using different. These encoders are all neural networks, and there is one like trainable encoder, variational encoder for each industry. For example, here, what is going on is the telecommunication data is being forward propagated through here via a variational encoder process. And after that, the encrypted lower dimensional embedding for the telecommunication encoder, like for these customers produced. Actually, the same procedure takes place in other industries at the same time. So after that, for example, there's a dimensional vector is produced for the telecommunication industry data of that customer, and B dimensional vector is produced for the same customer, but for the data from banking industry. So after that, we are concatenating all these vectors to feed these concatenated global encrypted input to the global neural network model. After that, this data is forward propagated through this global neural network model. So let me explain why I use variational encoders rather than like normal neural networks here. Because when one uses variational encoders, for example, here in the lower dimensional space, this cluster, let's say, it implies that the customer has good behavior. This implies that it has like average behavior. And this implies that it has like bad behavior in terms of the financial transactions. So now when we use the variational encoder, now these clusters actually continue so that a small perturbation in the data set wouldn't lead to huge errors. But if one uses normal encoders, like autoencoder rather than variational ones. Now these clusters would be, I mean, not continuous, so that small perturbations would would damage the model's accuracy. That's why I used. So for example, here you can see how these variational encoder, in terms of the cluster continuity is better than the autoencoder one. So let me briefly explain again. Firstly, we are making some pre-processing steps actually to prepare the data set so that the data representations are different for different companies in the same industry. After that, these data are one-hot encoded so that each company's data is specified. For example, if the data is coming from Türk Telekom or Vodafone, these encoder can know this so that it can optimize itself. So after centralizing this data in different, in different industries, beds of data are accumulated, and after that they are forward propagated through these telecom encoder. For example, for these telecommunication side, for bank side, they are forward propagated through this bank encoder, and after that this encrypted lower dimensional input vector for the global neural network is derived, and after that is forward propagated, and after that optimization part starts and global neural network model, and each of encoder is optimized accordingly via backpropagation. Key advantage of mix is the availability of use of all available data from various companies. Also, our data encryption steps match the data privacy regulations. So here I mainly made 3 different experiments. Firstly, I assigned the number of companies in each industry as 1, but for different number of industries, I compared the collaboration scenario with the scenario of when each industry uses only its own data to train the model. So I saw that each industry actually has an incentive to collaborate with other industries. I did the same experiment. Now there are just 1 industry, so no vertical splitting in the data set, but there are a varying number of companies. I again proved that they have the incentive to collaborate with other companies. And in the end, here you see the heat map. So here you see the number of companies. So vertical, horizontal split number. You see the number of industries, the vertical split number. So let's compare the case. For example, here 0.89 accuracy means that in our data set, we vertically split into three parts. So there are 3 different industries, and there are 4 different companies in each industry. And the average accuracy of the trained model is 0.89. But here it's 0.83. So our model, mixed method, is better outperforms no collaboration scenario. Actually, the results are more severe as the number of companies and the industries increases. For example, when the number of industries is 5, also the number of companies in each industry is again 5. You see the accuracy is 0.88. And in this no collaboration scenario, the accuracy drops to 0.75. So in the end, without violating any data privacy, we can make use of all the available data on the internet from different companies. Without violating the data privacy concerns, we can calculate the credit scores effectively. Thank you for listening.
Thank you, Mr. Efe, for this very interesting presentation. If there are any questions from the audience, you can write it to YouTube. I have a question, actually. My question is not a technical question. I just wonder, do you think that the industries will collaborate? Because you're saying that the data can be made anonym, right? So there is no violation of personal data violation, etc. So do you think the companies will collaborate? I mean, or do they will to?
Yeah, for example, in this scenario, there is just credit scoring, and actually only the banks have an incentive to make this collaboration with other companies, because Yemek Sepeti, I see Yemek Sepeti wouldn't have an incentive to make the Yapı Kredi's credit score calculation accuracy higher. But in this scenario, actually, they may agree that Also, banks would share its customers' data with Yemek-Sepeti in an encrypted way, and now they can train a model to actually calculate their customers, customers' behaviors for these for this delivery or food preferences in terms of the prices. So, like if Yemek-Sepeti accepts Yapı Kredi's offer to encrypt in an encrypted way, sharing its data to train the the credit scoring model. And in the opposite scenario, also Yemek-Sepeti can want the data from Yapı Kredi to train a model for its own purposes, not for credit score, for other purposes.
Okay. Yes, I understand. Thank you very much. Are there any other questions? Okay. Thank you for attending this conference, Mr. Efe.
Thanks for listening.
Yes. Thank you for your time. Now, sorry. Our next speaker is Mr. Özgür Çebi from Yeditepe University. And the topic of his talk is evaluation of behavior tree and finite state machine-based AI algorithms in shooter games. Okay, interesting topic. Yes, and the word is yours, Mr. Çebi.
Thank you. Let's share my screen. Okay. Good morning, everyone. I'm Özgür. I will talk about my research, which is the evaluation of behavior tree and finite state machine-based artificial intelligence algorithms in shooter games. So, artificial intelligence in games is considered as an important topic. There are many reasons for that, but most important ones are, firstly, most of the games require AI. Even if the game is played by multiple players, it's a must to implement an AI to make the matchmaking easier. And secondly, modern games use system resources at a high level, and this forces AI algorithms to use minimal resources as possible, which makes it harder to develop an algorithm. And the last reason is technological advancements. For example, Unity Engine has available frameworks for game AI, and Unreal Engine comes with BT algorithms built into the system. This makes it easier for developers to implement AI in their games. Scope of this research is shooter games. Since finite state machine and behavior tree algorithms are the most popular for implementing AI, they'll be compared. Finite state machines and behavior trees will be briefly explained here. A set of states exist in FSMs, which are connected by transitions. FSM can be represented as a directed graph where each node represents a state, and only one state can be active at a time. Whereas in behavior trees are defined as a directed tree which includes a set of nodes and edges. And while executing, each component defined in a BT is traversed and handled based on the conditions. A depth-first traversal is performed on each update until a low-level behavior is completed. Hence, behaviors are placed from left to right with respect to their significance. In video game industry, it is actually quite unclear for inexperienced developers to choose the right AI algorithm for a game. There are lots of AI algorithms on the table, and each have unique upsides and downsides. Since implementing and comparing all of them is hardly possible, this research includes two of the most used. For comparing the algorithms, a real-time shooter game is created with a game engine. The main mechanics of the game are implemented so that each agent uses the same rules, and this allows agents to compete in a fair environment. FSM and BT algorithms are implemented to the agents on different teams, and this way the data needed to compare the algorithms could be collected. The main factor in this data is the winner team. By analyzing this data, it's expected to get an idea to determine which algorithm is the best fit for a shooter game. I would like to talk about the design of the system. I will show state machine diagram for FSM agents and flowchart diagram for BT agents. This is the state machine diagram for FSM bot. I'm not getting into detail, but simply, algorithm checks if there's a target in range. If there is, agent pursues the target, and if there's not, agent wanders around the map. And when the pursued target is in attack range, agent attacks to the target. At the end, state machine returns to the initial state and the process is repeated. This is the flowchart for BT bot. It is simplified for explanation. BT bot starts the execution by checking if the agent is reloading or there are too many enemies nearby. If any of these conditions are true, agent retreats to a safe position to regroup with other teammates. If there are enough friendlies nearby to engage the enemy, BT checks if there is any valid target to engage. If there is, agent rotates to the target and starts to pursue. If there is no valid target, agent checks if the target is set previously to engage. If there is a target, agent rotates towards the target and checks if its weapon is out of ammo. If weapon has ammo, agent shoots at the target. Otherwise, agent reloads. If there is no target set to engage, agent wanders around the map until another condition is met. The whole process is repeated until the agent is terminated. I'd like to talk about the class structure of the system. This is the class diagram for FSM bot. The most important thing that I want to explain here is the structure of the game. As it can be seen, there's an AI logic that controls the decisions of the agent. However, core game mechanics are independent from this logic. That simply means an AI algorithm makes decisions but is bound with the same rules defined in the environment. This is the class diagram for BT bot. Notice that AI logic in the middle has changed. However, game systems stay the same. This allows the algorithms to evaluate their environment, make a decision, and use the game systems to accomplish that decision. Here are screenshots from the game. Agents are competing in a match. Map types can be seen here. They are used to measure the importance of the environment in terms of agent decisions. For testing the system, I conduct 18 tests. There are some test parameters that I want to explain. First one is map type. I conducted tests on different maps. The reason was that the map design could have an effect on the algorithm. Another variable is number of agents. Tests are conducted with 5, 10, and 20 agents. Last variable is include obstacles. When this variable is set to true, obstacles in the map are included. When it's false, obstacles are not included and both teams can see each other when the match starts. This is the average of the results on each test. To determine the success of an algorithm, 3 match parameters are watched. These are win rates, win time, and agents survived. Win rate is simply the win rate of the algorithm. Win time is the time it takes for a team to eliminate the other team. A faster elimination time is considered as an advantage. Lastly, agent survive parameter shows the number of agents survived in the winner team. If only one agent survives at the end of a match, that means the match went head-to-head. If all agents survive in the winner team, that means the winner won with extreme dominance. This is the data that I obtained in the small map. It is seen in this test that BT win rate is higher than FSM. Test 5 shows that BT win rate is 98%, which is very high. This is the test data for medium map. It is seen that BT win rate is higher than FSM. This is the test data for large map. BT win rate is still higher than FSM, but it is not as high as the small map. A decrease can be seen. It is seen from the test results that BT algorithm dominates the FSM algorithm in terms of win rate in almost all of the cases. Only exception was test 1, which was executed with only 5 agents in both teams. However, the randomness factor in the AI algorithms should be kept in mind, since most of the tests indicate that win rate of BT algorithm is much more higher than FSM. By adding 2 simple tasks, such as more effective enemy targeting and a flee action, BT algorithm wins most of the games. Despite the high win rate of BT, agents controlled by FSM algorithm could still beat BT agents with a dominance. However, these cases were very rare. It is also seen that as the map gets bigger, win rate of BT decreases. In terms of realistic shooter games, BT algorithm seems a better fit for AI agents rather than FSM. In the future, more AI algorithms could be added, implemented, and compared. I implemented only 2 of the most popular algorithms, but more can be obviously added. More intelligent decisions could be added to the agents, such as firing from covers, group movement with other agents, flank decision, shooting while moving, and so on. I implemented only 2 tasks, which are effective enemy targeting and a flee task, but more tasks would give a better result. Moreover, player-controlled characters could be added to the tests. Their reactions to the AI algorithms could be measured with surveys. These are the references that I used in the research. Thank you for listening. I can take questions now.
Okay, thank you, Mr. Chebi, for this interesting talk. Yes, the game programming and using AI in games is getting more popular. I mean, the game players, we do not know what's going on in the background, but the games get more competitive and more addictive to people, and this is probably the result of using AI in game programming. So you compared BT and FSM. That's what we have made, behavior tree and finite state machine, and it looks like FSM is not that good, right? That's the result that you obtained. But you said in large maps, the situation is kind of reversed. FSM can be good. So do you think that if you were, for example, making a larger map, maybe we will see FSM dominance? Do you think, or are you planning also to do that part?
Actually, it is seen that there is a decrease in the win rate of BT, but we cannot conclude that FSM will eventually have a higher win rate. I am planning on doing a test, but actually there are theoretical comparisons about FSM and BT, and it is usually said that BT is better for complex games, whereas FSM is better for simple games. This is because of the FSM is good for simplicity for easy games, and FSM lacks the maintainability. So you cannot reuse the states in other AI algorithms. But whereas in BT, it's possible to reuse a task in another behavior tree. So a larger map is in my plans, but from these results, I don't think that the results would really change. I think they will stay the same.
Then a follow-up question can be, I don't know, maybe I'm totally wrong, but then can I say that a larger map means a simpler game architecture because maybe the players are kind of more far away from each other? Is there such a thing, or is it maybe a very fast and wrong conclusion?
There are actually many factors. one of the reasons that FSM win rate is increasing in large maps could be agents are too far away, and the randomness factor in the AI could be kicking in. So the good side of BT is that it can retreat when engaging, so regroup with other teammates. But in a very large map, this may not be possible. So I don't think it's possible to conclude what you're saying, but I think it's worth a try to try it and implement it.
Okay, thank you very much again for your time and for that nice presentation. So let's move on to our next speaker, Mr. Onur Kirman from Özyeğin University. And the topic of his talk, the title of his talk is Handwritten Text Segmentation and Optical Character Recognition with Transformer Architecture. And yes, Onur, you can share your presentation and you can start.
Hi, let me share my screen. Okay. Oh, can you see my screen right now?
Yes, we can.
Okay. Hello everyone, I'm Onur Kirman, and today, okay. Hello everyone, I'm Onur Kirman. First of all, thank you for having me. It is a privilege to be here. Today I'm going to present my paper called Handwritten Text Segmentation and Optical Character Recognition with Transformer Architecture. This is the contents table that I will be following. First, about the paper. So we wanted a robust and accurate handwritten text line segmentation detection algorithm because ones that are being used are mostly utilizing old-fashioned methodologies. There are some conventional methods that can do this job, but they lack important parts, which is crucial in the OCR to have a modern and robust solution. For this purpose, we wanted to incorporate a new and highly effective method that can segment handwritten text lines using the latest computer vision and deep learning methods. So let's get to the solution part. First, we decided on the data set, which is called handwriting database that has 657 unique writers, and more than half of the writers have only one input image in the data set, making it quite challenging and robust against different handwritings. What do I mean by that is that every writer has submitted a single handwritten text image, so it is kind of a random handwriting type. You can see the pie chart of the writers that has more than 5 images on the right. Also, they are quite varying. Later comes the process. We have 3 sub-processes: pre-process, main process, and the post-process. In the pre-process, we change the size of the input into 256 by 256 resolution, dropped some insignificant parts, and added some patches, which are detailedly explained in the paper. So at the end, we got the image that is shown on the right. As grant-through data, we prepared what is called mask image using this table to gather bounding box information of individual text lines and created the mask image on the right for the particular row image from form image on the left. This table shows the distribution of data for train validation as processes, and you can see the distribution of the subsets usually on the right. So here comes the main process. We have 5 steps: loading data, building model, training, testing, and outputting. In the model part, we use different models and architectures. First, we introduce a solution with UNet model. It was the biggest improvement in the past period. has its unique shape and architecture that makes accurate predictions. In the first half of the U shape, it encodes, and on the other side, it decodes. It has convolutional block at every step and max spool or up convolution, depending on the encoder-decoder side between the blocks. You can see the visualization of the model here. And this is the total layers in the model that I used. After experimenting with the UNet model, we wanted to focus and keep researching on transformer architecture, which is why we used NLP model that started to gain popularity in computer vision due to some technological advancements. For this, we tried to come up with a new architecture that features not only what we already implemented and proposed, but also the transformer. After many research, we found a model called attention unit, which basically the unit with a couple more steps. It introduces a mechanism called attention gate. This placed just before the concatenation operations in the decoder side. You can see on the right, this gate acts as a magnifier to the focus area. The model can learn what to do even under the varied shapes and parameters. Also, in some regions, actually, it acts as a blinder of a model that helps the model to disregard the disoriented regions. Moreover to this, there was one more model called TransUnit that features the transformer, but this time in the encoder side. After CNN in the encoder, it makes a linear projection into transformer mechanism and reshapes the output to start the decoding part, which basically the same as in the UNet. This enables the model to predict better in localization. So these three models are used to propose our solution, and I will show their individual performances in the results section. These are the tools and methods that I used, Python for programming and PyTorch for any operation, basically. Also needed Colab for intense training. So validation. Validation is done using grant-truth image comparison. As I show you in the pre-process, the mask of the individual images compared with the predictions, actually. And every single prediction is compared pixel by pixel as shown in the figure by their indexes. Also conducted many different experiments to decide what parameters works or not, which was one of the most challenging because we need educated guesses to fine-tune our models for this particular task. This is later comes the post-process. Our solutions output mask images like shown on the left, and in post-process we basically detect the areas and put their rotation robust bounding boxes and output the image on the right for this particular prediction. Besides these, we added cats and dogs image patches to show that it is resilient against any other image 2 weeks actually. So here's the result section. The best model that has the highest score is the attention unit, but as you can see, it is not much a difference between the models on the table at the bottom because they already segment quite well. Grant-truth image is placed at the left-hand most and others according to the table order. If we look closer to this challenging input, for example, we can see that some text lines are improved significantly, even though the accuracy doesn't change much. This is the place actually where models differed other than accuracy rates. Currently, we have achieved to develop this particular benchmark with these accuracies shown on the table. And I'm continuing with the achievements. We achieved to develop working methods that does what we planned, actually, featuring the latest technologies that didn't take place before. Moreover to that, I wanted to compare things with already proposed to be a SOTA model, which is called Detection Transformer, DETR. I especially prepared this model to for this particular database. It is developed by Facebook AI. This model developed by Facebook AI and highly effective model for detection these days, featuring a transformer. But we can see that it lacks important parts of the input in the bounding box alignment, while our proposed solutions perfect fit over the lines. This is quite important because in the OCR we need to take care of these small details, because we are working on small details actually, so that it must be included in the bounding box alignment. But our solutions fits them perfectly fine. And also, there is one more thing about ETR. It is not robust against rotations. It requires perfect input in terms of rotation, while our models detect without any issue, as you can see from the figures. 90 degrees or 45 degrees rotation doesn't matter. It detects quite well. And this is the references that these are the references that I used. So thank you for listening, and now I can take questions if you have any.
Thank you, Mr. Kirman, for this nice presentation. Yes, and handwritten test, segmentation, and OCR were popular topics.
Yes.
And also kind of, I think, topics that have matured at a point, right? I mean, do you think that these problems in text recognition or text segmentation and OCR, do you think those problems are, I mean, these topics are kind of mostly solved, or do you think there are more way to go? I wonder your thoughts on this.
Yeah, as you said, there are lots of research and improvements done on this field, but we can say that some type of technological advancements are moving the edge computing part, where the computation is done over some instruments. So these instruments usually don't have that much power. So this transformer model and architecture provides an efficient and robust, easy to use environment for these particular edge cases, edge devices actually. So that we can actually reduce the performance requirements from the cloud to edge computers with these methodologies, which are almost it's perfectly fine with the current solutions actually.
Okay, are there any other questions from the audience? Just checking YouTube now. The live. Okay, looks like that's it. Thank you again for the presentation and for your time. And now let's move on to our next speaker, Mr. Orhan Eren Akgün from Boğaziçi University. And the topic of his talk is one-shot learning for retail product recognition. And yes, if you're ready, you can start, Mr. Akgün. Your microphone is not on.
Yeah, sorry. Let me just share my screen. So can you see my presentation?
Yes, we can.
Okay, so I'm starting. Hello, everyone. I'm Orhan, and my research is one-shot learning for retail product recognition. So I want to start with some retail terminology. SKU is a distinct type of product in retail terminology, such as Coca-Cola 330 milliliter can. This corresponds to categories or classes in other classification problems. And pack shot is a photograph of a product in a way to show that in a way that can be used to advertise the product, which should be visually appealing, as you can see on the bottom of my screen. So SKU recognition is the classification of SKU products based on their images or videos, and it has applications in self-checkout kiosks, automated shelf monitoring, and shop assistance for visually impaired people. And it has some unique challenges. It's a very fine-grained classification problem with minute discriminative cues on the texture. So you can see Ülker Bitter chocolate on the left, and Ülker Bitter pistachio chocolate on the left, and Ülker Bitter chocolate on the right, and they are visually very similar. And this leads to a low interclass variance. And also a diverse set of images can be obtained from the same object due to lighting conditions, partial occlusion by other products or price tags, motion blur, and object orientation. And usually number of SKUs is in the order of thousands. And it has dynamically changing classes due to frequent introduction of new products by the companies. And there is a possible domain shift between training or support image and test image, because sometimes only pack shot images of the products can be available before the test time. You can see on the left bottom of my screen a pack shot of a drink, a pack shot image of a drink, and you can see the shelf image of the same drink, and they are visually really different, and this domain shift can cause severe drops in the accuracies. So how should we approach the problem? The state of the art is to use convolutional neural networks, and CNNs can overcome most of the mentioned challenges when a large amount of data is available, but this is not usually the case for SKU image recognition due to frequent introduction of the new set of products. So the solution in the literature is the one-shot learning. Instead of learning to classify images from the ground up, we can use available dataset to extract prior knowledge that is useful on the target dataset. And usually a large dataset that consists of distinct SKUs is available, which can come from similar products of the same company or another company. For instance, you can see available data could be 3 chocolates of some brand with bitter milk and nuts flavor, and new introduced products could be pistachio and also bitter. So we can use the available data to extract prior knowledge to accurately classify the target SKUs. And I dealt with a particular scenario, and let's assume that we are a monitoring company, and one of our customers introduced a new set of products, which we call this test set, and we have only one image per SKU for this new set, and we call this support set. This image could be from the same domain from the test sets, such as shelf image, or they can be pack shot image. We also have a data set consists of other products of the same company. We will call this training set, and the problem is how do we accurately classify the new products? So our contributions in the paper is we provide a comparison of the methods on a realistic data set that carries most of the challenge in the SKU recognition problem. And we investigated the effects of intense domain shift between support and test sets. And also we experimentally showed that cosine similarity-based classifiers, which I'll explain in a minute, outperforms the CNN classifiers without introducing any training complexities, and it's also more robust to domain shifts. So I will give a more formal definition of the sets I used. We have a base set. It's a data set with large number of examples per SKU that is available during training. We also have a test set. This is the target data set we want to accurately classify, but this is not available during training. And the important thing is test and base sets do not have any common SKUs. They are distinct data sets. And we also have a support, or sometimes called prototype set, a data set that consists of one example for each SKU in the test set. And there can be a domain shift between support and test set image, such as the pack shot versus shelf image. And our aim is to utilize base and support sets to accurately classify images on the test set. So you can see we have base set and support set available during training. And the base set and test sets have different SKUs. And I used 3 different models to tackle this problem. The first one is the vanilla CNN classifier, the other one is CNN with cosine classifier, and the last one is variational prototyping encoder. A vanilla CNN classifier is just a traditional CNN classifier with 2 parts. Now, the first part is a feature extractor that takes an image and maps it into a 300-dimensional latent space. This feature extractor is realized with a 3-layered convolutional neural network. And the second part consists of a nonlinear neural network classifier, which consists of 2 layers, and there is a ReLU activation function between the first and the second layers. And we have 2 training states for this method. In the first stage, we train our feature extractor on the base data. And after that, we fix our feature extractor and reinitialize our classifier. Then we fine-tune our classifier on the support set, which consists of novel class data, and train a new classifier. And the second method is a CNN with cosine classifier. This method is similar to the vanilla CNN method. It also consists of 2 parts. The first part is the feature extractor part, which has the same architecture with the vanilla CNN part. The different part is the classifier. Instead of a dot product based 2-layer neural network classifier, we here use a cosine similarity based classifier, which takes which calculates the cosine similarity scores between the latent vector z and columns of weight vector w. And based on this cosine scores, we put these scores into softmax activation function and calculate the probabilities for each SKUs. And the training is the same with the vanilla CNN classifier, which consists of 2 stages. At the first stage, we train on base data, and the second stage, we train on the support set. So in summary, the both methods we have seen so far has 2 states. We take training set image, pre-process them, then we train a feature extractor and a classifier. We fix this feature extractor and train a new classifier on the second training, or sometimes called fine-tuning stage, on support set image. And the third method is variational prototyping encoder, which is based on variational autoencoder. And variational autoencoders, as you know, takes an input image and tries to reconstruct the input image itself again, based on some sampling in the latent space. And variational prototyping encoder just differs the last part. Instead of reconstructing the image itself, it tried to construct a prototype for that class. And this results in a slight change in the loss function of the variational autoencoder. In the original variational autoencoder, we have a reconstruction loss and KL divergence loss between the multivariate Gaussian defined in the latent space and a unit Gaussian. In the prototyping encoder, we just changed the reconstruction function to the generated prototype of that image and the actual prototype of that image. And what is a prototype? It's a single image that can represent its class visually, and a human observer should be easily recognize the class after seeing its prototype. And during the test phase, we map the support set image and a test image to the latent space via the trained encoder, and we perform nearest neighbor classification in the latent space. And as I explained, we used 3-layered convolutional neural network in the CNN methods, and we used the same network as the encoder part of the variational prototyping encoder method, and the decoder is just the symmetric of the encoder. And the data set, we introduced the Ülker data set here, which consists of RGB images with varying sizes that are ready for the recognition. What I mean by ready for recognition is that they are cropped, and there are 37 number of SKUs with 15,000 images in this data set. And I split this data set into 2, which are Ülker 19 and Ülker 18. I randomly selected 19 SKUs to construct Ülker 19, and the remaining 18 SKUs are Ülker 18. And we also have Ülker Digital, which consists of digitally crafted visuals of the products in the Ülker dataset. And we have one image per SKU in Ülker Digital. And in the original problem formulation, Ülker 19 corresponds to waste set, Ülker 18 corresponds to the test set, and a subset of Ülker 18 or Ülker Digital corresponds to the support set. So I dealt with two scenarios when there is no domain shift, where we selected the support set from a subset of Ülker 18. And also we have the case where we selected the support set from the Ülker Digital. And you can see the difference between the same product, Ülker Çikolatalı Gofret, when we selected the support set from Ülker 18 itself and from Ülker Digital. And here is the classification results we obtained. If we select prototypes from Ülker 18, VPE method performs the best, with slightly better than CNN with cosine distance. And when we selected the digital product image as support set, CNN with cosine distance performs the best. So experimental results suggest that all methods are affected by the domain shift between support set and test set, as you can see, but the CNN with cosine distance is the least affected one. And also changing from a dot product based classifier to cosine similarity based classifier can provide a increase in accuracy and also robustness to domain shifts. And thank you for listening. I would like to thank Professor Bülent Sankur and Dr. Erdem Yörük for their guidance, and thanks to Vispera for providing the Ülker dataset.
Thank you, Mr. Akgün, for this interesting presentation. Looks like the method you developed can be applied to different retail product recognition applications. Let me just check the YouTube channel, or I also have a question. Maybe I can just start by asking this. So you said that your data is pre-processed, right? Cropped so that we only see the product itself.
Yeah.
But of course, that requires some time and some other maybe some work somehow. Of course, it can be automated, but still.
Yeah.
So my question is, if, for example, the method that you're proposing, can be combined or can be applied to data sets which do not have, these crops. So basically, there's going to be a pre-processing, maybe, I don't know, with another algorithm.
Yeah.
Will that affect the methodology too much, or will that work fine?
Actually, the crops we used in the Ülker dataset are also obtained automatically using traditional detection algorithms. So our work can be combined with that kind of detection algorithms and can be applied in reality. But the scope of this work only included the classification part.
Okay. Do you plan to present this to those companies?
Actually, I developed this work under the supervision of Dr. Erdem Yörük, which is the CTO of Vispera, and Vispera is a monitoring company of the SKU products.
Oh, okay. So it's already being used somehow.
Yeah. Yeah.
Okay. All right. Thank you very much again.
Thank you
for this talk. And now we can, I think, move on to our next speaker, Ms. Eda Nur Var from Istanbul University, Cerrahpaşa. And the topic of her talk is prediction of students' academic success using ANN. If maybe I can use it when I'm trying to predict my students' success. So I will listen to this presentation carefully. Okay.
Eda didn't show up.
Ah, she didn't show up. Okay, thanks for pointing that. So I won't be able to listen to that interesting topic. So now let's move on to our next speaker, the actual group of speakers, Mr. Egehan Eralp, Mr. Abdullah Oğuz Türk, Mr. Kerem Solmaz. By the way, I will ask these students to, apply some image image processing, image improvement techniques to my camera so that it will better. My camera is not good. Please also consider it as a side topic. I will appreciate that. Anyways, the topic of the talk is sentiment analysis and reporting from text data in film reviews. Interesting topic. Yeah. So we can see your screen again, but yes, okay, now we can see the presentation directly.
Yes.
Now the word is yours. Thank you.
And yes, hello everyone, and welcome to our presentation. Our main aim in our study was to classify text data and perform a detailed analysis on it. So for this purpose, we prepared a scenario based on movie reviews, and we carried out our article study called Sentiment Analysis and Reporting from Text Data in Film Reviews. So now let's start the presentation. You can see our team, again, Abdullah Postuk and Kerem. Unfortunately, Kerem couldn't attend the conference today. Yes, and when we started this project, we had two goals. First one was developing a system where users can easily make a review on any movie they want and do not waste their time trying to give an appropriate rating. They won't waste their time because we will be doing the rating part for them. And how do we do the rating part? For this, we have trained and tested NLP models and compared the success of these models and used the most successful on your project. We will talk about these models in more detail shortly. And why do we have this goal? Because when we examined the text classification literature, we saw that most studies have classified text as just negative or positive. So we thought, like, why don't we broaden the study zone? And came to the conclusion that in addition to negative and positive, we can add more cluster in our study. Our second goal was to analyze the reviews made by users and report the results of this analysis to other users. So they can see if the movie suits the test or not with the minimum effort and maximum detail. We will also talk about this analysis. Yes, here we can see some examples of the methods we are using in our project that are also used in other studies in literature. Some technologies we used. And here are the libraries we mainly used, Pandas, NumPy, and Met libraries for data analysis and pre-processing. For classification models, we use scikit-learn and TensorFlow libraries, and Pickle for these storing these models. And NLTK for NLTK we use Jensen. For NLP we use NLTK and Jensen, and for data visualization we use Vertcloud and Matplotlib libraries. Here are the models we trained and used. For input representation we use WordTrack and DuckTrack, and for text classification we use logistic regression, decision tree classifier, layer bias, and RNN-STM models. Now we'll talk about system development steps, and I will pass the word to Egehan.
Okay, first of all, we divided the system into sub-steps with the divide and conquer technique. These steps are data and modeling, development of backend services and the application. Let's start with step 1 and examine its internal processes. As you can see here, step 1 basically consists of two different branches. The upper path is for rating prediction and the lower path is for positive and negative sentiment analysis. The first step of the processes is to collect the raw data. After that, we apply pre-processing to raw data. Then the clean text data is represented in vector space with input representation algorithms. Afterwards, several models are trained with document vectors. Then, according to the selected metrics, the most successful text classification model is determined and deployed. First, data was collected and prepared. In the dataset we used, there is 29,000 rows, approximately 110,000 unique words, and 10 output classes to predict. And we divided the dataset into train and test sets with a ratio of 80 to 20. Here, 100% balanced datasets are generated with the stratify parameter. After the raw dataset was transferred to the Python side, the pre-processing process has started. In this process, from the text data, HTML text removed, stop words dropped, capital letters convert to lowercase letters, punctuations have been removed, and non-alphabetic symbols have been dropped. Here we can see an example from our data set. The text data above is taken from the raw data set. As you can see, it contains capital letters, stop words, numbers, and punctuations. If we do not remove them, they will mislead the models by choosing each as a token during the analysis of the meanings of the words. So we clean all of them in the pre-processing stage and get the bottom text data. Okay, now our step 3 is input representation. The input representation is the process of digitizing a text input for the purpose of analyzing its meaning. In our study, we have used word-to-vec and doc-to-vec algorithms to generate word and document vectors. Here's an example from our system. As you can see in the image above, you can see a test review we made for a Titanic movie. To successfully analyze the meanings of the reviews in our system, we defined a 200-dimensional vector space and represent our sentences in this space using the doc-to-vec model. In the image below, it is shown the input text data represented with 200 values in the system. So now our models will classify text over these vectors. Okay, the input representation is done. Now it's time to mention about modeling stages. First, let's look at rating prediction models. Within the scope of our study, text classification is carried out using decision tree, naive bayes, and logistic regression models from the scikit-learn library, and the LSTM model from the TensorFlow library. At the training of these models, the parameter values in the tables you see on the slide were used. After the training stage, these models predicted ratings for test data. Okay, let's evaluate each model results. We use confusion matrices and the accuracy metric to evaluate the models. First, let's examine the predictions of the decision tree model. Confusion matrix shows a near diagonal predictions at rating above 5, but there is unsuccessful predictions at low ratings. And since the accuracy metric is 45%, we can say it is an insufficient model for text classification. Let's look at the naive bayes results. Actually, regardless of the actual rating, it produced a prediction as a 1 with high rate. And in this case, the rating 1 has been overfit in the learning of the model. So even if the accuracy is higher, it is not a model that can be used in real scenarios still. Let's continue evaluating. In the confusion matrix of the logistic regression model, there is a much more successful distribution on the diagonal compared to other models. Real test data and predictions seem to be quite compatible, except for the ratings 3, 4, and 5. And the accuracy is almost 65%. Therefore, we can say that it's a model that can be used in real scenarios. Finally, if we look at the LSTM results, here the prediction results did not show an acceptable confusion matrix. Rating 2 and 3 are almost never learned, we can say. Therefore, this model cannot be used in production either. After the evaluation of the rating prediction models, the most accurate model is determined as logistic regression. Then this model was deployed to Google Cloud Platform for use on the backend side. As you can see in the general process, the upper part is now completed. Now comes the modeling steps for sentiment analysis, and I pass the word to Oğuz again.
Thank you again. And sentiment analysis is to predict whether text input content is positive or negative. For this, we first had to reduce the number of output classes in our study to 2. So we marked the text data with 1, 2, 3 ratings as negative, and text data with 8, 9, 10 ratings as positive. And we came to the modeling stage by following the pre-processing and input implementation steps that we mentioned before. In the modeling phase, we use decision tree, naive bayes, and logistic regression models from scikit-learn library. These models are trained with the parameter values you can see on the table. The reason why we don't use LSTM here is that the neural network training takes too long time, and the results are not very successful. So now let's look at the evaluation of these models. First, let's examine the predictions of the decision tree model. In the confusion matrix, the sum of false negative and false positive gives us 657 pieces of data. Therefore, the accuracy is 81%. If you look at the naive bayes result, false positives are few and optimal, but false negatives are too much in this naive bayes result. In other words, text data with positive content couldn't be analyzed as desired, and the accuracy is also 90%. Finally, let's examine the logistic regression results. The most successful confusion matrix was formed here. Total of false positive and false negative predictions are 267. Therefore, the accuracy metric is calculated as 92.3%. After the evaluation of the sentiment analysis models, the most accurate model is determined as logistic regression. Then this model was deployed to Google Cloud Platform for use on the backend side. If you look at our overall process diagram, all data and modeling work is now complete. And next, we have the second step of our project, developing backend services. And I will tell you about this step. For our backend services, we used Python and Flask web framework. We have two main services. The first one is our sentiment analysis service. As you can see in the schema, this service takes movie review as input and apply preprocessing on this text data, then detects the keywords in the text data and store them in the data frame created for the movie. At the same time, after the preprocessing, using the TUAC model, it represents the text data as 200 valued vector. This vector is then given as input to the classification models we have deployed. As output, rating and sample predictions are obtained from these classifications. These outputs are written to the data frame and stored in the cloud and simultaneously sent to the user as service outputs. Our second web service is visualization. These services were reporting the results of movie reviews analysis to the users. And let me tell you about its working steps. It takes movie name as an input. It gets the data frame corresponding to the movie name. First, it reads the keyword column from the data frame, then analyze the frequency of keywords. With the results of this analysis, it generates a word cloud. Then with data from ratings column, our rating is calculated and generates a rating bar chart. Finally, from the PN column, positive negative column, it gets the data and calculates positivity rate and create a bar chart. Word cloud, average rating, positivity rate, rating bar charts, and positivity bar charts are reported to the users as output. Here you can see a sample data frame that we have stored in the cloud. The original review made by user kept in the text column. The keywords obtained after preprocessing is kept in the keywords column. Our prediction of ratings and positive negative sentiments are kept in the rating and PN columns. As I said before, our main aim in our project was to classify text data and report a detailed analysis. For this purpose, we have prepared a scenario based on movie reviews. We developed a simple mobile application within this scenario. Finally, we would like to show you a demo video of our application.
Okay, here's our demo video. Okay, let me show you. There is applications interface, as you can see. There are several movies listed, and user chooses the movie that he or she want to make review. Let's see. Okay, this review made. And the results reported to user, rating is 6/10. Sentiment is negative right now. He wants to see the reporting. As you can see, there is bar charts. Rating bar chart, positivity bar chart, average rating, positivity rate, and the word cloud picture. Yes. This can be every movie, as you can see. Let's go to Blade Runner. And that's it. That's it. Thank you for listening and including us to this conference. It was a priceless experience for us. Thank you.
Okay, thank you, Mr. Eralp, Mr. Oğuztürk, and Mr. Solmaz for this presentation and for your time. I think we have a question from our audience. Maybe you can ask now.
Thanks, guys. That was an excellent research, and I very well aware of this study, actually, to some extent. But I have two questions. First one is, do you guys have any idea to extend this into podcast region so that the text basically is actually automatically generated by, for example, some sort of software like YouTube or so, and then take that transcribed version and then apply it to your algorithm? Because in podcasts generally, since I'm very well interested in this basically realm, I want to understand, for example, in a nutshell, okay, what is this guy talking about? As you said, is this a sentimental blah, blah, blah, whatever. So do you guys have a plan to extend into podcast analysis? Because they have very well transcribed. And the second question, let me just ask in bulk, am I going to be able to, see that app, on GitHub or this kind of stuff? Because I know that you guys are contributing to open source. So if you can answer these two questions, I would appreciate it. Thanks.
Would you like to?
Oğuz, are you speaking or I can speak?
Or you can go.
Okay, first of all, for your second question, yeah, of course, we will share it on GitHub or Kaggle notebook. And also, we're gonna share the data sets. And you can download or clone on your local and experience to yourself. For your first question, this should be done, as you said, because the text data is everywhere, we need to augment the text data with different topics, different domains, and see what this project working on them or not. We have to do this, and we're gonna do this, I think. What do you think, Oğuz?
Yeah, we should really do this.
Okay, thank you.
Are there any other questions? Okay, I don't have any further questions, and it looks like the audience does not have as well. But I should say that I'm quite impressed by the app that you showed at the end. I congratulate you for your research and showing off some results of it. So thank you again to this group as well. And now I think I can close the session. It was the Sunday morning session. We are a bit like 15 minutes out ahead of our time. I'm sorry, delayed, but that's still fine. So thank you, and our next session will be at 2 p.m. today. Just to let you know, to our attention.